In a typical setup for learning robotic navigation, an agent is given a representation of the current state from which it predicts a steering command, such as go forward, turn left, or turn right. In this work, we present a new action representation for mobile manipulation, which we call spatial action maps. The main idea is that we can represent a set of possible actions using a pixel map, where every pixel is a navigational endpoint at the corresponding scene location. This allows us to use a fully convolutional network to map from state images to actions, such that the actions are spatially anchored on local visual features of the scene. Our action representation has several key advantages compared to steering commands. First, the agent is not myopic. It can move directly to endpoints in a single action, which enables goal-driven behaviors. Second, a complex navigation trajectory can be represented by a single action. In contrast, if we use steering commands, a complex trajectory would require a long sequence of actions, resulting in sparse rewards for learning. Third, the action space lies in the same coordinate space as the state, so there is a direct mapping from states to actions. Together, these advantages enable faster learning of complex behaviors for mobile manipulation tasks. To study our new action representation, we consider a setting where an agent is tasked with exploring an unseen environment, finding objects, and pushing the objects into a designated receptacle. We train our agent in a pi-bullet simulation environment. As the agent moves around in the simulation, it uses a forward-facing virtual camera to perform online mapping. It starts with a blank map and gradually builds up a global overhead map, which contains everything it has observed. The agent also builds up an occupancy map, which is used to compute global shortest path distance maps. To construct the agent's state representation for reinforcement learning, we take oriented crops of the global maps to generate local maps. These local maps are spatially aligned in the robot's local coordinate frame, such that the robot is always positioned in the center and facing up. At every step, the agent feeds the state image into a fully convolutional network to produce a dense pixel-aligned Q-value map, which encodes the expected future reward of moving to every endpoint location. The agent then finds the action that maximizes expected future reward and executes it. Here we show some qualitative results in the real-world setup. We observe several emergent behaviors learned by the robot. The first is pushing well-positioned objects directly into the receptacle. However, this does not happen frequently. The most common behavior is to first push objects up against the walls and then use the walls as guides. The walls allow the agent to push the objects across very long distances without slipping, and is especially useful for pushing multiple objects at a time. Another emergent behavior is pushing through corners. Objects easily get stuck in the corners, which the agent handles by nudging the objects or backing up and trying again. We also investigate trade-offs of different algorithms in the simulation. Here we compare our method with the steering command's baseline and find that the baseline is unable to learn effectively in any of our test environments. For more details, please check out our paper or visit the project webpage.